this antenna has to be deployed, which was our main radar antenna, which is used for imaging. Now that signal didn't come. So that was expected to become within the 30 minutes. What has happened is that when the satellite was moving, it was going out of our Indian visibility. Then we have a Earth station at Mauritius. We have arrangement with all our international ground station with different countries. So whosoever visibility that satellite is, that signals will go to that station, and from there it is relayed back to our Bangalore center, where we will do the analysis. So in between the transition, for few minutes, that takeover was lost. And in that position, what signal came there was that this antenna is not deployed. That means there is some problem in that hinges have not opened properly or something like that. You can interpret it in different ways. What status signal has come is that these antenna panels are not yet deployed, which was supposed to be deployed at this particular location. Then immediately we were all worried, although some of our colleagues were celebrating that it's a successful launch and everything went on very smoothly. Some few knowledgeable people were just trying to figure out that why this signal has not yet come to us. Immediately after that, it was rectified and it was due to only a telemetry signal. Signal actually has come from satellite to the ground station, but it was not relayed back properly to our Bangalore center. So luckily everything went on very smoothly, and finally the satellite, as I mentioned, is working very well the last 1 year. And this is what is happening at other station. Satellite is launched from Sriharikota, which is near Chennai. We have at Bangalore, which is a commanding station from where we control this satellite, and its telemetry is observed all over the world at different ground station. And something is happening in our Hyderabad Earth station. That is where the data which is imaged by this sensor is received at Hyderabad center. And there we are generating the images out of this data, because radar data is like that. In your camera data, once you click your camera, you get the image. You don't have to do any processing. But in radar, it is like that. If that signal you just try to display it on your TV screen, it will happen like if you switch on your TV screen without any signal connected to it, what you will see is some snow-like structure, some noise dots are moving. Something similar will happen. If you don't process it properly and you just display that data on the screen, it will appear like that white or snow noise. So for that, what you need is a very elaborate processing system. So here we have around 240 digital signal processors, each having some 1 gigaflops of operations capability. This is one of the world's highest capacity digital signal processor, and such 240 are working in tandem in parallel to generate this sort of images. So and this too is done in real time. So as signal starts coming, this data is being processed, and as a scrolling image, it will appear on your TV or a display screen. Now coming to the societal applications, I can have another 20 minutes? 10. Okay, so now coming to where we will be applying all this data or signals which we are receiving from all these sources. So this is where agriculture is there, or disaster monitoring is there, or forestry is there, or flood mapping is there. So all these areas are being covered by this particular sensor. And not only this sensor, all our optical sensor about which I mentioned earlier, they are also useful in one way or the other. In fact, last 20 years, we have been working with all these optical camera systems only. They only were doing all these applications. Now this radar system has augmented, further strengthened these application capabilities. So you can see we can have agricultural, forestry, environment monitoring, geology, exploration, infrastructure and utilities. Nowadays all these 3D city models, lot of these towers are coming up for our mobile communication and all. So doing survey for that also satellite pictures are being utilized. So where to lay out, have your tower which in a more effective way so that you end up with less number of towers and a more effective coverage. All these things, utilities is being covered with a high resolution imaging, as that is mentioned in the infrastructure and utilities. Similarly, cartography, mapping, and then national security. So all these applications are met by all these sensors which I was mentioning. So to give an example, say this digital elevation model, that is one requirement. So not only the normal area, plus say Mount Everest, Himalayas, all this mapping also being done, and we can measure even the height of the targets on the ground itself using this what you call a stereo imaging. So you view a target or area from two different angles and try to find out the height of that object or the target. So that is one application. Similarly, we have a big earthquake in 2001 in Kutch. So what has happened to that earthquake area before that, after the earthquake also. So you try to compare those images and try to find out the new, what was the ruin, what was the damage, basically for damage assessment and other, so that you can take accordingly rehabilitation measures. As I mentioned, you cannot predict or try to find out earthquake because that L and S waves which are being generated, they are too weak or too feeble to be picked up by any even earth sensor or even satellite sensor. So till now that maturity has not come, but at least you can do post damage assessment and work out the relief and other measures. So that was one application area. Then this is a routine work of crop inventory modeling and production forecasting, because as you know, India being an agriculture economy predominantly, you need to government all schemes or whatever societal measures or benefit for poor people, what they work out in advance or budget it during the budget session in March or during the revised estimate in September. They need all this information. Without that, they cannot plan out different schemes. So based on all this forecasting, how the crop is going to be there, Rabi crop or Kharif crop. So for all this information, all these imageries are being utilized. Then you have, as I already mentioned, earthquake damage. You have a high resolution imagery to work out landslides and what was the damage due to the earthquake. So this is all post damage assessment. And then this particular satellite I just wanted to mention because it was called third world satellite, and it had now all these satellites what earlier I mentioned, big satellites, low earth orbiting, you can receive data only at the earth station, big earth station like we have in Hyderabad. But I have this mini satellite where even a user like college students or any other researchers can download that data through their small VSAT terminal and get this data. So that's why that was the first time this was tried out in this mini satellite. So we have apart from big satellite, we have a series of mini satellites which will be regularly coming up, and it will have a small sensors which can be utilized for different type of research and other projects also. Then I mentioned about these oceanographic applications. So these were two, it was a unique in a sense that you have one optical camera system, what we call ocean color monitor, and you have a spectrometer radar system. So it can detect on an ocean surface by the movement of your waves, because that is governed by the wind which is blowing. So wind modulates the shape of the waves which is there on the ocean. So that you try to detect from the height of 700, 800 kilometers and find out what was the wind at that time in that area on various oceans of the earth, all oceans, not only our Indian Ocean or Bay of Bengal. And that is a very important information because it feeds into all our meteorological models, and it can be utilized to predict what will be the weather. Because all of you know, whenever our weather prediction comes, we don't believe it because we are sure it is wrong only. But there are reasons for that. It is not that our scientists are not capable of predicting weather, because tropical countries face this problem. There are so many variables and parameters. If one of the parameters is wrongly estimated, you end up with a different scenario compared to what actually will happen. But we have seen in USA or Europe, if they predict it will rain today, it will rain exactly at that same time. But that is not happening here because of all these reasons. And for that, what you are missing is we are trying to basically fill by doing such applications. So this can detect winds over oceans. And this was one application I wanted to mention it because before trying out in satellite, similar system we developed and put it in an aircraft which was flying at 8 kilometers to 15 kilometers, and then it is used to generate images in real time using such, as I mentioned, DSP based processor. So immediately you can start. So basically that's why its name, it is SHARP or disaster management, because in disaster what you need is the time coverage is very important. Wherever disaster, immediately you have to map it. So pre-flood and post-flood assessment mapping is to be done, and then based on that, this information goes to the ground or the taluka level to the district collectors, so that they can, because they are the people actually on the ground. They have to be fed proper information based on which they can take correct decision and take correct measures. So that's why this utility of that. And one major thing which we detected, say there was a Kosi river breach. But that river breach has occurred in Nepal. Okay, and I am in Bihar because our border is Nepal-Bihar border. If I want, but the problem due to the breach is occurring is in Bihar. Now, if I want to find out that, I have to fly over Nepal. If my system, this particular radar system, but if it is another international nation. Now, if I have to fly that way, it goes through, as you all know, taking permission from all 100 types of agencies, because you want to fly in the territory of another nation. So you can imagine the problems. So what we did is, we modified our system in such a way that a look angle has been verified so that it looked at a very steeper angle, to a very far angle, and while flying over Bihar, we could image over Nepal. So that was the beauty of this particular expedition which we carried out. And in fact, we measured actually what was the breach, total 1 or 1.2 kilometers breach was there. From that data after processing, and the major striking feature was that we flew over our Indian region and tried to assess the damage which has been done on a part which was situated in another nation. So this is how the flood maps are generated based on the radar data. Then it is put on actual maps, and then this information goes actually to the taluka or the district level for the actual government agencies which are working there. And then we have what you call a rice, as I mentioned, Kharif and Rabi crop predictions and all that. The movement of the growth of the crops, that is being monitored on a routine basis of different areas, and that is used in forecasting the overall crop yield for that particular year or for that particular season. So that is one major application. And this is how we moved in radar imaging, that we started with a resolution of 20 to 100 meters in radars. And today we have reached a system which can do up to 1 meter imaging. So again, and because radar, as I mentioned, to show you the complexity, how complex it was, this is a big achievement within these next 25, 30 years. And this was, now before we launched our satellite, in between, because of our security needs, we also had another satellite hired from another external country. And that was called RISAT-2 radar to take care of our strategic needs. So that was the radar which has been bought out from actually Israel. And it has served purpose. It has completed 3 years, being regularly utilized for various applications. And this is how what I was trying to tell you about, how radar is different from an optical camera system. The above we have shown is a camera image where you see a lot of cloud cover. So whenever there is cloud cover, you don't see beneath that what will be there below this particular area. So there are a lot of white patches, we don't have information about that. In radar images, it penetrates through this cloud and you get the images. So both these things complementarily together can help you do better applications in a better way, basically. So that is the purpose of, so basically these microwave sensors as well as optical cameras, they complement each other and supplement in many cases, and that way we can now do all our applications in a better and a more methodical way. These are some of the images we try to compare with the Google images of this satellite which I have shown. This is some Himalayan glacier region. This is Sundarban Delta and Northeast region. And all these I am showing because all these areas are fully covered by cloud or rain is happening, and during that period we can take images and get good information out of that. So that is the beauty of this whole, this is one glacier. So these all pictures have been taken in last 1 year or so. This is the area of Mumbai. So you can see all your ceilings and other areas. This is of Gujarat. And some of you people who are interested in learning more about this, recent current science publication has full details about all these further technical details. Although I have bored you with much technical details, but if somebody is further interested in learning about that information, applications, everything is available here, right from starting this concept up to the applications, where all it is being utilized and useful. And current science has recognized our capabilities, and as a gesture they have put all these articles from all our engineers. I think I'll just 2 minutes I'll take, because Mars or Chandran I will not cover, because I'll leave this my presentation here. People interested can go through that, or if you want, if you. So this Mars orbiter mission is going to be launched in October 22. I'll come to that. But why explore Mars? Somebody can ask that, because many people have done that earlier, USA, USSR. Why we should do that? As you know, Mars is almost very much similar to Earth. It has been deprived of atmosphere. There are problems there, very high temperatures, very low temperatures. So whether Earth can also meet similar fate, that is one worry all of us. Although it is not going to happen within our lifetime, or in all of your lifetime also. But still, scientists are interested in knowing, and if, as you mentioned now, our Earth resources are getting depleted. So whether we can move on to some other planet, which is the likely planet. Mars is the only one which looks more or less habitable. So to meet all these objectives, this mission has been started, and we will be flying it, launching it through our PSLV launcher, because that is a well-proven one. As you all know, it has almost 99% of success record till today. And the only problem is that Mars is very far off, 400 million kilometers from here. And since Earth and Mars both are moving around Sun, you have to find out the ideal time to launch, so that you end up there when without much effort, or with spending very less fuel, so that you can achieve the Mars orbit. Because otherwise the distance goes on varying. So that's why I'll go to the next one. So how we are going to achieve that? So we have 5 different sensors there. So methane sensor is one of them. So whether some organic life is there on that planet or not, that will try to find out. So this methane sensor has to work with accuracy or sensitivity of 1 part in 1 billion. You can imagine the sensitivity of this sensor which is being put. Requirements. Then you have alpha photometer, which will try to find out that hydroxyl molecule. So whether water exists somewhere in Mars atmosphere or surface or not. And then you have imaging spectrometer to study the geography or the topography of the Mars red planet. So these are the different sensors being developed at different places. 3 of these sensors are developed at our Space Application Center, Ahmedabad. And one is from PRL, another one is from SSPL VSSC, that is Trivandrum. And then it will have launch on 22nd October. Now, what is the sanctity of this date? It is very essential and urgent that we launch it on this date or nearby date, because as I mentioned, it will take 1 month to go to the Mars injection, and you can see after going to Mars also, it will have a very highly elliptical orbit, 500 kilometer by 80,000 kilometer. Right now, all our satellites on Earth move at around, say, 600 kilometers or 700 kilometers, almost circular orbit. Here it will be highly elliptical. So sensor sensitivity also has to match that, because if it is this far and trying to map something on that planet, you can imagine the sensitivity required for that sensor. And then the other problem is, 1 month it will take to go into a transitory orbit, and after that it will cruise. So you have a ascent and then cruise and then final Mars orbit injection. So totally, if you see, it is almost 9 to 9.5 months of duration. So I will launch it, and we will always be happy that it has been launched. But finally, whether it has reached there and acquired the Mars orbit or not, and if we miss out something doesn't work properly, then it will go on and on. It will disappear into our galaxy. So that is the problem we'll be facing, and almost, I think, I don't remember the exact numbers, but 9 or 10 out of total 18 or 19 missions to Mars till date by various countries have failed to inject it into this proper orbit around Mars. So that is the complexity we will be facing, but our people are working very hard on that, and we are very much confident of success for all this. And the other, what I was mentioning, why this date is urgent, if I miss this out, I cannot launch it. I have to launch now, wait to up to some September, October 2016. Even if that date I miss out, then 2018. So you can imagine the problem. So that's why I was mentioning that this whole mission we are trying to complete within 10 to 11 months only, after we got government approval to work on this. until this launch date, which is nearby more or less fixed only. You cannot vary it too much. So if you miss this out, I will have to wait 3-4 years for doing my next attempt. And the reason for this is that Mars and Earth, since both of them are moving, next slide also. So this is the principle behind that why it is like, since both are moving and there are two different methods. So basically you can have 260 days or 220 days based on the whether it is you are having an orbital conjunction or opposition with Earth. And then the problem here is that, the problem is this. Say my PSLV has a limited weight carrying capability. As I mentioned, my RISAT-1 satellite was 1858. That is the maximum capability with full resources it can put into the orbit. Now here, since we have to go far, that limit is 1350 kg. Now in that, almost 800-900 kg I have to put fuel only, because I have to reach up to that point, and in between there will be a lot of corrections where fuel will be utilized. So whatever sensors I am putting, I can give you example of my RISAT radar. Out of 1858, 950 was my sensor weight or payload weight. Rest was satellite and fuel and other things. Here, out of 1350, only 14 kg sensor is there. Rest of all is satellite plus. So when it is finally put into Mars orbit, that satellite will have only 500 kg of weight. Rest all is being used up because that is the fuel part of that. So that is being used up while it is being taken from our Earth. It has gone to the cruise mode and then reached the Mars orbit. And if everything works out successfully and it achieves Mars orbit, it will have 500 kg of weight. So you can imagine, because say normally some other countries like USA will not face this problem because they have a bigger launchers. So once our GSLV works out fine, which is expected within next few months, then we can also, we need not worry about these launch dates. But right now, if we have to, since we are tied up to the PSLV launch, we have to ensure that it happens on 22nd October. If we miss out that, after 3 years. So that is the complexity of this particular mission. But all of us are very hopeful and we will have enough confidence and capability that we will succeed in this. Just briefly, I will touch upon, I will not go why we should do lunar exploration. So we have different methods. So this was our Chandrayaan-1 mission, which was launched on 2008. Again, it was first time. I can mention that till now, all the other 6-7 space countries who have launched this satellite to moon, all of them have failed on first attempt. But India was the only country which succeeded on the very first attempt. So that was also a big achievement. And that also prompted us to go for our next mission, because if you see in the first mission, we had only 5 sensors from our ISRO, and rest all were international sensors, that is collaborative sensors. Many people have sensors or different subsystem ready, which they offer it on a collaborative basis. They are put on no cost basis on our sensor, and we can get data out of that sensor. So that is the agreement, cooperative agreement between different countries. So out of all these sensors, we have only limited sensors available. So this was Chandrayaan-1. And it has achieved all its goal. Although it was supposed to work for 2 years, it worked for almost 1 year, and there is some snag developed. But still, it has fulfilled most of its mission requirements, and that capability exists now with India to launch its satellites to moon. And that only prompted us to go for this Mars mission and all. So these are all steps one by one which we are taking up. Now with Chandrayaan-2, now as you all know, that finding out water molecule, that was one big achievement of that particular mission. And now to further strengthen that signature and find out what really is the things going on moon and whether we can habitate that moon in near future. For that, further studies are required, and for that, this Chandrayaan-2 is being designed. And then one other major improvement over there is that we are going to now put a lander and a rover. Means we are going to have a soft landing. In Chandrayaan-1, we had, some of you remember, we had thrown a camera from that satellite onto the moon. But that is called a hard landing or a crash landing. So it just went and hit that target, and there was a flag, Indian flag painted on that, and it crash landed on that particular moon surface. But this time what we are going to do is that, because we are thinking in a long-term future, we want to put human beings on moon. In that case, you cannot have a crash landing, then everything will disappear. What we need is a soft landing, And soft landing, how you can do soft landing? Say like your pilots eject out of your aircraft, that is a soft landing. But there is a parachute which takes care of that. Because atmosphere is there on Earth. Now on Moon there is no atmosphere, parachute will not work. Otherwise that is the simplest method. You put something with a parachute and just dump it, it will slowly go and glide and it will have a soft landing. But that luxury is not available to us. So there are different methods how to go about the lander. So what we work, this is the basic configuration of that. So this is how that satellite will look. It will be stored and put into, it looks like a robot walking. So, and it will have all these applications, and this will be put into a satellite and launched, and then lander will separate out. How it will do, I'll just show you pictorially. We'll not go into the instrument. There are different instruments available in different frequency band. Almost they are similar to your camera system, radar system, everything is there. So this is how the lander will be looking like. So initially what happened was, lander was to be provided by Russia. In fact, that agreement still is there, but last 1 year back, they developed a problem in one of their subsystems. So till they solve that problem, they are not ready to provide us this lander. So as I mentioned, every problem has some opportunity. So we seized upon that opportunity, and parallelly now ISRO itself is working on developing a lander. We have worked out the configuration, and we are hopeful of meeting all the requirements, and we can have now our own lander which will carry one rover or a robot, and which will be detached and landing. So this is that rover which will come out. So first lander will land, have a soft landing on the moon surface, and out of that this rover will come out and do some experiment and relay that signals back to Earth. Yeah. So these are the different, I will just show you this, how this lander is going to land, soft landing. So this is how the once the satellite is in Chandrayaan orbit, say at 100 kilometer by 100 kilometer over moon area. So this is how that whole structure, out of that this lander will separate out. Orbiter will go on orbiting like a satellite around moon, and lander will have this type of soft landing. So there are different instruments which will monitor its landing. They are within this lander. And then it will have what we call it will hover around some place. Right now, if you know, there are a lot of craters and other canyons and other things on the moon surface. So that has to be avoided, so that it doesn't land into one of these craters, then everything is lost. So this is how it will have a soft landing after collecting all information and deciding on its own where to land. And then this rover will come out of that. And then once it's doing experiment, we have this different communication links. So sitting on Earth, we can command both lander, rover as well as orbiter to carry out different tasks. So this is how it has been envisaged. So I'll end at this, and if any questions I'll take. Before that video I'll just show you. So we have different instruments. Just I put some details about these instruments because I was thinking that spectrometer may interest some of you people. So that is part of our orbiter also, and then it is part of our rover also, where we do some experiment when the rover will be moving around 500-meter area around that lander. So that much area, and that whole mission will last for 15 days. So all that experiment after landing on moon with lander and rover will be done for next 15 days. And then finally orbiter only will be in picture. That will work for under 2 years. It will collect images and send it to Earth. So these are the different instruments. This is one Indian, like you have now your mobiles. On your mobiles, if you want to get position, velocity and time information, that all will be also be available. So ISRO has planned out a 7 to 11 satellite configuration. So this also, I call it, these are also extended eyes in the sky that will help further strengthen all this total monitoring scenario over the Indian region. I'm thankful to all my colleagues who have helped with that. And Before I move to video, just 1 minute I'll take, sir. Please pardon me. I showed you only the part of the vision what Dr. Sarabhai told initially. But what he told was that we do not have fantasy of competing with economically advanced nations in the exploration of moon or the planets or manned space flight and all that, and we'll use technology to solve societal problems. So some of you may say there is a contradiction in what we are doing today and what was supposed to be Dr. Sarabhai's vision, but it is not like that. I want to emphasize that all these we have achieved because we have progressed on technology, acquired and mastered the technology, and it is not only benefiting society, because some of the work which we have done for these science missions like Chandrayaan or Mars, that directly feeds into our remote sensing or other communication and navigation satellite system. So in a sense, they are all complementing and supplementing each other. So as Mahatma Gandhi has said, that the future depends on what we do in present. We are trying to improve our future by doing all these things, although apparently it looks contradictory, but it is not like that. And